Hello everyone, welcome to our YouTube channel Electronics Maddie. In today's video, I'm going to explain the working of a three-phase inverter operating in 180-degree mode. This is the circuit diagram of a three-phase inverter. If you carefully observe the circuit and compare it with a single-phase inverter, you will notice two additional thyristors are being used. Due to the inclusion of additional two thyristors, we will be able to achieve conversion of DC into three-phase AC. It sounds surprising, but after looking at this video, you will know the importance of each of these thyristors in the circuit. But something that you have to remember is with respect to the modes. There are two modes with respect to three-phase inverter circuit, that is 180-degree mode and 120-degree mode. The mode indicates the duration of conduction of each of these thyristors. What does that mean? If I am saying 180-degree mode, each thyristor or switch will be conducting for a duration of 180-degree mode. That means the total duration is basically 360 degree and each of them will be conducting for at least one complete half cycle. So that is for 180-degree mode. Whereas in case of 120-degree mode, each thyristors will be conducting for 120 degrees. We'll be taking a look at 120-degree mode in detail in my next video. Over here, I am considering a star connected load so that the analysis becomes simpler and you can even try it for delta as well. Now, in order to convert DC into three-phase AC, you need to trigger these thyristors in a specific fashion. And this triggering concept is what we call as conduction sequence. So the pattern of conduction of these thyristors is basically in this particular fashion. 561, 612, 123, 234, 345, 456, and then 561 repeats again. The total duration is 360 degree, and after every 60 degree, one of the pattern of conduction of thyristor changes. If you carefully observe, from 561 to 612, 61 remains the same, whereas 5 is turned off and 2 is turned on. That means one thyristor will be turned off and another thyristor will be turned on. And if you carefully observe, if you're considering 180 degree till 180 degree over here, one is here, one is here, one is here. So basically, thyristor 1 will be conducting for 180-degree mode. And so again, if you carefully observe, 2 is here, 2 is here, 2 is here. Again, 2 is conducting for 180 degree. So in this way, each and every thyristor will be conducting for a total duration of 180 degree. And that is why this mode is called as 180-degree mode conduction. One important thing that you have to note is, let's consider one particular conduction sequence, that is 561 is turned on, that is thyristor 1, thyristor 5 and thyristor 6 over here. The power supply is connected in this particular fashion to the load. So the green one indicates the flow of power. If you carefully observe over here in the circuit, when these thyristors T1, T6 and T5 is conducting, they will basically act as short circuit, isn't it? Because it is a switch. Consequently, DC supply flows through the star connected load. So one thing that you have to remember here is, how is A, B, C connected to the battery? This is very important for our analysis and we will be making a note of it. So the inference is basically A is connected to the positive plate in this particular fashion because T1 is connecting over here and the current flows through this path, and that is why it is connected to the positive terminal of the battery and it is indicated over here. Whereas if you consider B, B is connected to the negative plate because T3 acts as open circuit. So you will not have a flow of current through this path and hence the current flows through only this path. And as a result, B is connected to negative terminal of the battery and C is again connected to positive terminal of the battery. So this ABC is basically three-phase output that we will be achieving. And that is why this is very important. Make a note of this inference at some place because this is very, very important for us to draw the equivalent circuit. So what is the equivalent circuit for 561 conduction? So A was connected to the positive terminal of the battery, C was connected to the positive terminal of the battery, and B was connected to the negative terminal of the battery, isn't it? So I'm rearranging the circuit because all the other switches over there was either open circuit or short circuit. So the open circuit we have totally ignored. only short circuited with respect to thyristors we have considered, and we are able to draw the circuit. I hope this concept is clear up to this point. Now what we will be doing is we will start our analysis. So at the first step, we need to find the current I flowing through the circuit. How do we find that? So it's very simple. First, we will be finding the effective resistance of this particular circuit. So if you carefully observe, R equivalent is basically R into R by R plus R, because these two resistors are connected in parallel. So you'll be getting R square by 2R, and R gets cancelled. You will be remaining with R by 2 at this point. So the effective resistance of R and R connected in parallel is basically R by 2. But I is given by V by R, isn't it? According to Ohm's law. V is nothing but Vs over here, which is the supply voltage, and divided by the total resistance. We got the effective resistance at this point as R by 2 plus R. So R plus R by 2 is the overall resistance in order to find the overall current flowing through the circuit. I is equal to 2 Vs by 3R. So we have got this. So why is this current important? It is very, very important because we need to find the voltages, that is VAN, VCN. So VAN is basically the phase voltage across A, and VCN is basically the phase voltage with respect to C. So the line voltage is basically directly given as VA, VB and VC, whereas the phase voltage is given as with respect to the neutral. I hope this concept is clear. So VAN is equal to VCN is equal to, because if you carefully observe, both are connected between the same 2 points, isn't it? So the voltage will be the same because the resistance values are also same. That is why VAN is equal to VCN, and which is basically I into R by 2, the effective resistances. So as a result, if you substitute the value of I that is found out previously, you'll be getting VS by 3. So now you know VAN and VCN. So you're getting it as VS by 3. Whereas VNB, that is this voltage, is given by I into R, that is I found out was 2 Vs by 3R, and R is substituted as it is. RR gets cancelled out and you will be remaining with 2 Vs by 3. But what we want is VBN, not VNB. So we will be simply getting VBN by reversing its polarity, isn't it? Because according to a convention, if this is positive and minus, and if you're measuring the voltage between these 2 points, then the voltage will be opposite in polarity, isn't it? So that is why you're getting minus 2 Vs by 3. So this is an important observation. Why are we doing this? That is a big question, isn't it? So it's very simple. So over here, one important inference will be drawn from these equations. What is that? If two phases are connected to one of the terminals of the battery, then the voltage is nothing but Vs by 3. If only one phase is connected to one terminal of the battery, then the voltage is 2 Vs by 3. This is very, very important, and this will give us a very important inference and a shortcut, because we cannot derive this for each and every case, isn't it? For 561 we have found out. Again you have to find it for 612, 123, 234, and again the pattern repeats. For each of these circuits, drawing the equivalent circuit is very, very complicated, and you cannot do this in a sequential manner, right? It takes a lot of time. So as a result, there is a shortcut in order to remember this. How can we analyze that? So if two phases are connected to the supply, then V phase, P basically means if it is A or C or B, depending upon whatever you want, you will be substituting PH, that is basically the phase voltage, that is Vs by 3. If they are connected to the positive terminal of the battery, then it is Vs by 3. If they are connected to negative terminal of the battery, then it is minus Vs by 3. So in this case, A and C was connected to positive terminal of the battery, and both the phases was connected to the same point, and that is why we are taking it as Vs by 3, as it was connected to positive terminal. Similarly, we have one more analysis, that is if one phase connected to the supply, then we'll be giving the voltage as, or getting the voltage as 2 Vs by 3. So that is, in this case, we got VBN as 2 Vs by 3, isn't it? Basically minus 2 Vs by 3. So what does that mean? V is actually connected to the negative terminal of the battery, and that is why we wrote it as minus 2 Vs by 3. If it was connected to the positive terminal of the battery, then we would have written it as 2 Vs by 3. The polarity would have been positive. Make a note of this inference. This is very, very important. and I will tell you how this is very important in drawing the waveform. So as a conclusion, we got VAN is equal to VCN as Vs by 3 and VBN is equal to minus 2 Vs by 3 for 561 conduction. Now what we will be doing is we will be drawing a table, and this table will give us an indication on how do we draw the waveform. So how do we arrive at this table? It's very simple. When 561 was conducting, what happened? We got Vs by 3, Vs by 3 as VAN and VCN was same, and we got minus 2 Vs by 3. This is done. How do we analyze it for 612? Now in the circuit diagram, 6 is conducting, 1 is conducting, and 2 is conducting. If you carefully observe, 6 and 2 is connected to the same terminal of the battery, that is B and C, isn't it? So B and C voltage should be Vs by 3, but they are connected to the negative terminal of the battery, and that is why it is minus Vs by 3. Whereas A alone, that is with respect to A phase, 1 is conducting. So it is connected to the positive terminal of the battery through 1. As a result, the voltage is 2 Vs by 3. I hope this concept is clear. Again, we will be doing it for 1, 2, 3. Slowly observe this. 1 is conducting and 2 is conducting, 3 is conducting. 1 and 3 are with respect to A and B, isn't it? So when two thyristors are connected to the same terminal of the battery, what we will be saying, the voltage is basically Vs by 3. And since they are connected to the positive terminal of the battery, we will be getting Vs by 3. Whereas C is connected through 2, isn't it? And it is connected to the negative terminal of the battery. 2 is connected through this fashion as 5 is acting as open circuit. So 2 is connected to negative terminal of the battery, and since only one phase is connected to the negative terminal of the battery, you will be getting minus 2 Vs by 3. So you're getting VCN as minus 2 Vs by 3. I'll be doing it for one more case. For 2, 3, 4, if you carefully observe, 2, 3, 4. So basically 4 and 2 are connected to the same terminal of negative terminal of the battery. So you'll be getting it as minus Vs by 3 and minus Vs by 3. I've written it over here. Whereas in case of B phase, if you carefully observe, because of 3 is conducting and it is connected to the positive terminal of the battery, and only one phase is connected to the positive terminal, you'll be getting 2 Vs by 3. And it is positive terminal connected to the battery, and that is why I'm writing it as plus. I hope this concept is clear. Similarly, do this analysis for 3, 4, 5 and 4, 5, 6. And once you get this table, drawing the waveform is pretty simple and straightforward. You can blindly draw it. Let's look at the waveform. I'm considering the table just for you to look at the waveform. So basically we have three phases, VAN, VBN, VCN. And now what we are going to do is we are going to start the plot. So these are reference lines. Initially this is Vs by 3. I'll be labeling it later, but the voltage waveform is Vs by 3 for VAN. Just observe this column. Vs by 3 and then it goes to 2 Vs by 3. It is going to 2 Vs by 3. This is 2 Vs by 3 and then it comes back to Vs by 3. We have got it back, and then it goes to minus Vs by 3 and then it goes to minus 2 Vs by 3 and then it goes to minus Vs by 3. So basically you are getting the exact waveform with respect to this column. Vs by 3, 2 Vs by 3, Vs by 3, again goes to minus Vs by 3 and then minus 2 Vs by 3 comes back to minus Vs by 3. So this is how we have to draw it for the waveform with respect to the table. So once you are having the right table, drawing the waveform is not at all a challenge. A lot of people have confusions with respect to drawing this waveform. So I expect you to not make any mistake because you know how to draw the table. Now how do we draw it for VBN? Observe the table. It should start from minus 2 Vs by 3, isn't it? So you're getting minus 2 Vs by 3 and then it goes to minus Vs by 3 and then it goes to Vs by 3 and then it goes to 2 Vs by 3 and then it goes to Vs by 3 and then it goes to minus Vs by 3. So basically you are starting from minus 2 Vs by 3 going to minus Vs by 3 going to plus Vs by 3 and then 2 Vs by 3 and then Vs by 3 minus Vs by 3, exactly according to this. And how do we draw for VCN? You're going to start from Vs by 3, go to minus Vs by 3 and then minus 2 Vs by 3 and then minus Vs by 3 again and then go to plus Vs by 3 and then go to plus 2 Vs by 3. Now you might be asking me a question. How does this change take place instantly? Like why not we are not having a slowly increasing curve, or why not we are not having a sinusoidal nature of a curve? That is something that you might have as a doubt, isn't it? So since we are using resistive load, the variation takes place instantly. But if you are using an inductor, the change takes place slowly. We cannot write this as a rapid waveform. So totally depends on your load. I've considered a resistive load, basically a star connected resistive load. As a result, the changes takes place instantly. Hence it's a spike. It just changes rapidly. I hope this point is clear. Now what is the line voltage? How do we find the line voltage? V line. So I'll be doing it for VAB. VAB is found by VAN minus VBN. So in this waveform, you have to subtract these two and you will be getting the final waveform for VAB. And you will have to do it for VBC and VCA. I expect you to do it. It is pretty simple and straightforward. So how do we find VAB? As I told, VAB is basically VAN minus VBN. So if you carefully observe, VAN is Vs by 3 and VBN at this interval is minus 2 Vs by 3. So Vs by 3 minus 2 Vs by 3 will be giving you Vs, isn't it? So it will be Vs up till this point. Why is it so? If you carefully observe, 2 Vs by 3 minus of minus Vs by 3 again will give you Vs. Hence from here to here it will be Vs. What happens at this point? Here VAN is Vs by 3, VBN is also Vs by 3. Vs by 3 minus Vs by 3, you will be getting 0. So you are going to get 0 at the output voltage. Consequently, what happens during this point is that you're getting minus Vs by 3 minus of plus 2 Vs by 3. You will be getting minus Vs. As a result, it will remain minus Vs till this point. You have to do it for this one as well. Minus 2 Vs by 3 minus of plus Vs by 3, you will be getting minus Vs. So you're getting minus Vs. At this point again, at this interval, minus Vs by 3 minus of minus Vs by 3, you will be getting 0. As a result, it goes back to 0 and the cycle repeats. This is the waveform for VAB, that is obtained by VAN minus VBN. This is the line voltage waveform and these are phase voltage waveform. Now you might ask me, where is the AC output waveform? Normally everyone thinks AC waveform means it should be sinusoidal in nature, isn't it? This is a common thought process that I had as a student as well. But what is the major difference over here? So although it is a stepped waveform, there are different processes of converting this stepped waveform into sine wave. So if you carefully observe, it resembles like a sine wave. Just observe the movement of the cursor. It resembles like a sine wave. So basically we can convert this stepped square wave waveform into sine wave by using filters. You can use LNC elements and you'll be able to convert that into sinusoidal waveform. I'm not going in much detail with respect to it, but this is a three-phase output waveform. I hope this point is clear. Just to justify that, I am explaining that. And this nature of waveform, we call it as quasi square wave. And this waveform, we call it as stepped waveform. So what is the conclusion as a whole is very, very important. Like if you are writing this in an examination, you need to remember some important points. As a whole, what are the inferences that you can draw from this? Each thyristor conducts for a period of 180 degree. First important observation. Each thyristor is triggered at an interval of 60 degree. Again, we covered this as well. At a time, 3 thyristors are conducting. We saw that in the conduction sequence. I hope this is also clear. Phase voltage is 3-stepped waveform. We got the phase voltage waveform as 3-stepped one. Line voltage is quasi-square waveform. We again got this as well. Maximum amplitude of phase voltage is 2 Vs by 3, isn't it? Because we got the maximum amplitude to be equal to 2 Vs by 3 and another amplitude that we got was Vs by 3. Comparing Vs by 3 and 2 Vs by 3, 2 Vs by 3 is much greater than Vs by 3. And that is why the maximum amplitude of phase voltage is 2 Vs by 3. Whereas maximum amplitude of line voltage is Vs. So some of the most important inferences over here, make a note of it in a separate place. And this is how you need to analyze the working of a three-phase inverter circuit. I hope this point is clear. You were able to understand the working of a three-phase inverter operating in 180-degree mode. In case you have any questions, feel free to reach out by typing in your questions in the comment section below. If you like this video, please do like it, share it and subscribe to our channel for regular updates. Thanks for watching. Please do keep supporting. Thank you.